So far in the last discussion on Markov chains, what we had been able to do is resolve the issue of existence and or uniqueness of stationary distributions for any irreducible Markov chains. Essentially what we have seen is that for an irreducible Markov chain, there are three possibilities: either all states are null recurrent, all states are transient, or all states are positive recurrent. And in the first two cases, we know no stationary distributions exist. And in this last case, that is when the Markov chain is irreducible, positive recurrent, we do have a unique stationary distribution. Of course, in the case additional situation when the Markov chain has only finite number of states, the first two contingencies cannot arise. So it's necessarily true that for such a chain, namely irreducible finite state space, we always have a unique stationary distribution. Now in this module, what we're going to do is we're going to study some examples and see, first of all, whether or not there is a stationary distribution. We'll only look at irreducible cases, and then see how we can find out those unique stationary distributions in cases they exist. So first two examples will be finite state space, and then we'll move on and see some infinite state space irreducible Markov chains also. The issue of existence, uniqueness of stationary distributions, we've completely settled for irreducible Markov chains. So what we know about irreducible Markov chains is that either all states are transient, or all states are null recurrent, or all states are positive recurrent. Now in the first two cases, no stationary distribution exists. In the last case, that is when all the states are positive recurrent, a stationary distribution exists and is unique. Moreover, the unique stationary distribution pi is given by this formula, that is for any x in S, pi x is 1 over ex tx, that is expected return time to x starting from x. Of course, it is positive because the states are positive recurrent and therefore the denominator is finite. So in particular, you see that pi assigns strictly positive mass to each x in the state space. Of course, if the state space is finite, the first two cases do not arise, because if you have an irreducible Markov chain which is finite, then all states are positive recurrent, and therefore there is a unique stationary distribution. So that is a very special situation with finite state space Markov chains, provided they are irreducible. Okay, let's consider some examples having seen the theory. So here are some examples of irreducible chains, and we'll examine existence of stationary distribution and find it when one exists. So here's example 1. We consider a Markov chain with state space 4 states, 1, 2, 3, 4, and the transition matrix given by this 4 by 4 matrix. Okay, from the transition matrix, you can easily see that 1 leads to 4. Clearly, in one step, you can go from 1 to 4. And then from 4 to 3 also, you can go in one step with positive probability. Similarly, 3 to 2 and 2 to 1. And therefore, by transitivity, all states leads to every other state. So, this is an irreducible Markov chain with finite state space, of course. There are 4 states. And therefore, by what we have just now seen, it has a unique stationary distribution. So the question is, what is this stationary distribution? We want to find it. So for that, what we are going to do is we are going to appeal to the definition of stationary distribution. Remember, by definition, stationary distribution pi is supposed to be a probability on the state space 1, 2, 3, 4, which satisfies this matrix equation. Of course, this matrix equation pi equal to pi p is just, if you expand it, it's just the following 4 linear equations in the variables pi 1, pi 2, pi 3, pi 4, and they look like this. From the last 3 equations, you can do a little bit algebra, and you can derive that pi 1 is 10/9 of pi 2, pi 3 is 4/3 of pi 2, and pi 4 is 3/4 of pi 2. So pi 1, pi 3, pi 4 have been expressed in terms of pi 2. What next? Well, normally you would substitute these things in the first equation to solve for pi 2 and then get the other values. Unfortunately, that doesn't work, because when these are plugged into the first equation, you end up getting only an identity in pi 2. So there is no question of solving for pi 2. So what do we do? Well, this is something that you should always remember when finding the stationary distribution. What we need to use is this additional fact that pi is a probability on S, which means the numbers pi 1, pi 2, pi 3, pi 4 must add up to 1. So now if you use the fact that pi 1 is 10 9ths of pi 2, etc., in this additional condition, then you can solve for pi 2, and once you solve for pi 2, you get the values of the others. So you end up getting these values of the probabilities pi 1, pi 2, pi 3, pi 4. So you have actually found the unique stationary distribution completely. Now recall that in general pi x is supposed to represent the reciprocal of ex dx. So once you find the unique stationary distribution, you also in turn get the values of this expected return times. So in particular, E1 T1 would be the reciprocal of pi 1, which of course is 89 by 20, and so on. So you actually, once you solve for the stationary distributions, from that you also get values of the expected return times for each state starting from that state. So here's an important remark. So in this example, we had 4 linear equations in 4 variables. What we did was we used the last 3 equations to express pi 1, pi 2, pi 3, pi 4, pi 1, pi 3 in terms of pi 2, but plugging these in the first equation gives an identity. So what that means is that the 4 equations by themselves have infinitely many solutions. Okay, that is, you can take any value of pi 2, any real value of pi 2, and then use the other equations to get pi 1, pi 1, pi 3, pi 4. So all these things would be solutions of that matrix equation. Is it surprising? Well, it shouldn't be, because anyway, if you look at the matrix equation pi equal to pi p, it is after all a homogeneous system of linear equations. So to find the unique stationary distribution, we have to finally use the additional condition that summation pi x equal to 1 in addition to the matrix equation pi equal to pi p. So what's important here is that this is going to be always the case in general. That is, just the matrix equations would never give you the value of the stationary distribution uniquely. You have to also somehow use this additional condition that the pi x's add up to 1 in addition to the matrix equation pi equal to pi p. Okay. So let's go to another example. So keep that in mind. This is the Ehrenfest diffusion chain which you have seen. So this is a Markov chain with state space 0, 1 through up to d. Remember, the d is the number of balls distributed in 2 urns, etc. And the transition probabilities are given by this. X to x minus 1, probability is x by d. X to x plus 1, probability is 1 minus that. Again, the state space is finite and the chain is clearly irreducible. You can convince yourself. So to find the stationary distribution pi, again we'll consider the equations pi equal to pi p, which is equivalent to, if you expand it, the matrix equation, it's a bunch of linear equations, pi y equal to summation x, pi x p x y. Now the equation for y equal to 0 would be, so let's try to write this equation for each value of y. So if you take y equal to 0, the equation becomes simply pi 0 equal to pi 1 over d, because all the other px zeros for x other than 1 would be 0. So from this you end up getting pi 1 is d pi 0. Next you look at the same equation for y equal to 1. Now you would get pi 1 equals pi 0 plus 2 pi 2 over d, again because for y equal to 1, pxy's are all 0 except x equal to 0 and 1. So 0 and 2, and therefore you get this equation, which again you can do some algebra and get pi 2 equal to d into d minus 1 pi 0 by 2. So you see, what we have been able to do is we have been able to express pi 1 in terms of pi 0, pi 2 also in terms of pi 0. Now my claim is that in general for every y you can express any pi y for y from 1 through d in terms of pi 0, and this turns out to be the formula. And the proof is by induction. That is because for y with y up to d minus 1, the equation is this. So assuming, as in induction hypothesis, that the result has been proved for pi y and pi y minus 1, then you can easily get the result for pi y plus 1 from this equation. So that's something that you can easily check. So therefore what we have is that for every y from 1 through d, pi y has been expressed in terms of pi 0, and the formula is pi y is d choose y pi 0. So we have now used the d minus 1 of the equations to get a formula expressing pi y in terms of the pi zeros, all the pi y's in terms of pi 0. Again, as in the previous example, we have to now use this additional condition that pi is a probability on S, which means the pi's add up to 1. Now remember that all the pi 1, pi 2, etc. up to pi d have been expressed in terms of pi 0. So this condition would actually boil down to using this pi y equal to d choose y pi 0 in this, and then you get pi 0 into 1 plus d choose 1 plus d choose 2, etc. d choose d equal to 1. So from that you end up getting the value of pi 0 to be 2 to the minus d, and from which all the pi y's become d choose y 2 to the minus d. So we have obtained the stationary distribution, unique stationary distribution, and this should look like a very familiar probability distribution. So this is a stationary distribution for this Markov chain, and it's exactly the binomial distribution. If you remember the binomial distribution, this is a binomial distribution with parameters d and half. Again, as in the last example, now that we have obtained the pi y's, from there we can get the values of ey ty, the expected return times, simply by taking reciprocal of pi y's. So the two examples that we considered were both examples with finite state space irreducible Markov chains. So we didn't have to worry about existence of stationary distribution. We already knew that there is a unique stationary distribution. Our job was just to find it. Now we consider examples of irreducible chains with infinite state space. So unlike in the finite state space case, now the existence of stationary distribution is not guaranteed anymore. So what better example to start with than the simple random walk with infinite state space? So the state space is all integers, and remember the transition probabilities are you go from x to x plus 1 with probability theta, and x to x minus 1 with probability 1 minus theta. Of course, we assume that theta is a number strictly between 0 and 1, which will make the chain irreducible. So what about recurrence, transients, etc.? As we have seen already, that if theta, that probability theta, transition probability theta is not equal to half, in that case we have already seen that all states are transient. So therefore in that case there are no stationary distributions, so we don't have to worry about that case at all. We already straight away conclude that there is no stationary distribution for the chain in case theta is not half. So the only case to be examined is the case when theta is half, that is symmetric simple random walk. Of course, in this case all states are recurrent, so there still is this question, is there a stationary distribution? Of course, we know that there would be if the states were positive recurrent or null recurrent, but directly deriving that would be difficult. So let's straight away try to see if there is a stationary distribution. That will answer also the question of whether states are positive or null recurrent. Of course, a stationary distribution pi has to satisfy pi equal to pi p. And now if you write this matrix equation as system of linear equations, what you end up getting is that for every y in Z in the state space, pi y has to be half pi y minus 1 plus half pi y plus 1. This is just because you can only come to the state y from y minus 1 or y plus 1, each with probability half. But this equation is equivalent to saying that pi y plus 1 minus pi y is same as pi y minus 1 for all y in Z. So if you denote, so that means that the successive pi y's, the common difference is the same. So denote that common difference to be delta. So say delta is pi 1 minus pi 0. Then of course you all know the formula for sum of an arithmetic progression. So you end up getting pi y equal to pi 0 plus delta y for all y in Z, which means we are able to express all the pi y's in terms of pi 0 and the common difference delta. So if we can find the common difference delta and find the pi 0, then we can find the stationary distribution. Now the condition is we have to have pi to be a probability, which means that summation pi y has to be 1. Unfortunately, if pi y is pi 0 plus delta y, then summation pi y can converge only if both pi 0 and delta are equal to 0. So that means that all the pi y's are 0 for every y, which means that if you have any solution of pi equal to pi p, then the only solution happens to be pi y equal to 0. Only solution which is a probability is pi y equal to 0. That is, no solution of that equation would have a convergent sum. So we conclude that there are no stationary distributions. Of course, in turn that really means that all states are null recurrent, which means that return time to any state y starting from the state y is always infinite. So for simple symmetric random walk, if it is not symmetric, all states are transient, and if it's symmetric, then also no stationary distribution. That means all states are null recurrence, which means that for random walk there is never going to be a stationary distribution. Simple random walk. Okay, so that's our first example with infinite state space. Let's now go to the another infinite state space Markov chain that we have seen. I'll call it IID replacements at successive breakdown. So there is one part in a system which has a random lifetime, and when it breaks down, it's replaced by an identical item the very next day. So we have seen this particular at time n, xn is the age of the unit that is in operation on day n. So that's the Markov chain. We have seen this Markov chain before. So the state space is 1, 2, 3, 4, etc. The age of the running machine on day n can be 1 or 2 or any positive integer, and the transition probabilities are given by this formula, or of course recall that L is a positive integer valued random variable assumed to be unbounded. So L really is a generic notation for the lifetime random variable for each of these successive replacements, and we assume it to be unbounded, which means that for any x, probability that L greater than or equal to x is positive. This is just to ensure that we have an infinite state space Markov chain. So recall that as I said, this particular Markov chain arises in the context of a system that runs on an item with random life, and when an item breaks down, it is replaced by a new item at the start of the next day, and the successive replacements are assumed to be IID lifetimes and represented by L, and x is the age of the item in operation on day n, and xn is a Markov chain. So with the assumptions, we have already seen that this particular Markov chain is irreducible and recurrent. Since the state space is infinite, there is either a unique stationary distribution or no stationary distribution, depending on whether the states are positive recurrent or null recurrent. So unlike in the previous example, where we tried to solve for a probability pi on S satisfying the equations pi equal to pi p, here we will directly examine positive null recurrence of states. So the approaches are different for different examples. So we know enough to check one state for positive and null recurrence, because in an irreducible Markov chain, either all are positive recurrent or all are null recurrent in case they are recurrent. So we consider state 1 and ask whether 1 is positive recurrent or null recurrent. Equivalently, whether E1 T1 is finite or E1 T1 is infinite. So note that for this particular Markov chain, being in state 1 means that we have a freshly installed item. The age of the unit in operation is 1 means that that item has been freshly installed. So starting from state 1, the time to return to state 1 will therefore be exactly the time that a freshly installed item takes before it's replaced by a new item, because when it's replaced by a new item, again the state would be 1. So the first time the state would become 1 is when a freshly installed item breaks down and it's replaced by a new item. So therefore, the time for the Markov chain starting from state 1 to return to state 1 is exactly same as the lifetime of a fresh item. So if you are convinced of that, then you can easily see that E1 T1 is nothing but E of L, expected lifetime of a typical unit. So that state 1 and therefore each state is positive or null recurrent according as EL is finite or not. So whether expected lifetime of a typical unit is finite or not will determine whether all the states are positive recurrent or null recurrent. So here is the conclusion. If EL is infinity, that is expected lifetime of individual items is not finite, then all states are null recurrent and therefore no stationary distributions. On the other hand, if the expected lifetimes of a typical item is finite, then there is a unique stationary distribution, and you can verify that pi x is given by probability L greater than x divided by EL, and that comes from this easy conditions. Pi 1 is 1 over E1 T1, which is same as 1 over EL, and for any x greater than or equal to 2, you consider this matrix equation pi equal to pi p. If you look at the corresponding linear equations, for x the equation is pi x equal to probability L greater than or equal to x divided by probability L greater than or equal to x minus 1 times pi x minus 1, because you can come to x only from x minus 1. And now, so you have expressed pi x in terms of pi x minus 1. Now if you continue this recursively, you end up getting that pi x for any x is going to be probability L greater than or equal to x times pi 1, and therefore since pi 1 is 1 over EL, you have the formula for pi x, any pi x. So that takes care of this particular Markov chain. Let's now go to queuing chain. So recall that the queuing model with one server, at the start of a time period, if the server finds any customers waiting for service, then only the first customer in the queue is served during that period. Otherwise, there is no service during that period. And we assume, so there is no randomness as far as that is concerned. The randomness here comes from this, that arrivals during successive time periods are assumed to be IID, non-negative integer valued random variables with common distribution. I call the generic random variable of number of customers arriving as xi. Probability xi equal to z is theta z for z equal to 0, 1, 2, 3, etc. So essentially, for any unit time period, the probability that z many new customers arrive for any z 0, 1, 2, etc., probability of z customers arriving is theta z. So suppose xn is the number of customers in queue at the start of the nth time period. Xn is a Markov chain, and the transition probabilities are given by this. This is something we have seen. Now recall, so we want to examine its irreducibility first, and then in case it's irreducible, we want to examine existence of stationary distribution. First of all, therefore, we have to rule out the non-irreducible situation, and we have seen before that in the two cases when either theta 0 is 0, or if theta 0 plus theta 1 is equal to 1, then the chain is not irreducible. So we need to only consider, if we want to consider irreducible Markov chains, we need to only consider the case when first of all theta 0 is positive, but at the same time theta 0 plus theta 1 is not equal to 1, less than 1, strictly less than 1. So the chain is now irreducible, and therefore now we are in a position to ask legitimately the question as to whether there is a stationary distribution or not. So for proceeding further, let's assume mu to be the expected number of arrivals in a unit time. So it's E of xi, which is summation z theta z. So what we are going to prove is that if mu is greater than 1, then all states are transient and therefore no stationary distribution. That is something that we had already been seen. The other case is when mu is less than or equal to 1, we have shown that all states are recurrent. So we need to only consider this case, namely when mu is less than or equal to 1. The question is, are states positive recurrent or null recurrent? under the situation that mu is less than or equal to 1. Because if mu is greater than 1, we already know that the states are all transient. Okay, so assume mu less than or equal to 1. And as before, it's enough to examine any one state. So let's examine state 0 for positive or null recurrence. So the question is E0 T0 finite or E0 T0 infinity? From Markov property, you can easily see that E0 T0 would be 1. That is, either you could go from 0 to 0 in one step, or you could go from 0 to any other y and then go from y to T0 using Markov property. But then remember that one time unit has already been lost. We have discussed this before. So you get this equation. So now my claim is that Ey T0 is same as y times E0 T0 for all y greater than or equal to 1. Why is that? This is a consequence of really two observations. For every y greater than or equal to 1, the Py distribution of T0 is the same as the sum of y many IID random variables distributed as the P1 distribution of T0. So we'll examine this. And the second fact is that P1 distribution of T0 is same as P0 distribution of T0. So once we have these two facts, it's easy to see why Ey T0 would be equal to y times E0 T0. Because first of all, Py distribution of T0 can be, under Py, T0 can be written as the sum of y many IID random variables. So therefore, Ey T0 would be the sum of y many, expectation of y many identically distributed random variables, also independent. So it will be y times that. And these random variables are supposed to be distributed as the P1 distribution of T0. So therefore, the common expectation would be E1 of T0. But this second observation would say that E1 expectation of T0 is the same as E0 expectation of T0. So that's how it follows. So let's see. The second fact is fairly easy to see. By Markov property, you can see that P1 probability that T0 equal to n for any n is P1 0 plus, so in one step you go to 0, or in one step you go to y greater than or equal to 1, and then starting from y you take n minus 1 additional time to return to T0. So but on the other hand, P0 probability of T0 equal to n is P0 0 plus this. Now this fact that P1 T0 equal to n is same as P0 probability that T0 equal to n follows from the fact that transition probability from y1 to any y is same as the transition probability 0 to any y. That's because of the very special nature of the chain. For the first fact, observe that this Markov chain, the Markov chain can come down anytime only by steps of 1. And once the chain starting from y reaches y minus 1 for the first time, it starts afresh from y minus 1, independently of what has happened in the past. That is the Markov property. So let's see the argument for y equal to 2, and then for argument for any y is similar. So let's see, P2 probability that T0 equal to n. First of all, by Markov property you can write it this way. In order to come to 0 starting from 2 in n many steps, you have to come to 1 first starting from 2 in some m many steps, m less than or equal to n minus 1, and then you have to go to 0 in n many steps. But then by using Markov property you can easily see that that is same as the second sum, which boils down to the third sum, because the first factor is no different from the fact, P2 probability that T1 is m is same as P1 probability that T0 equal to m. So this second equality, that is the equality of these two factors, that P2 probability that T1 equal to m is same as P1 probability that T0 equal to m, comes from the Markov property and the fact that, as I said, the Py probability that Ty minus 1 is m, that is the probability that starting from y, the time to return to y minus 1 is m, that probability does not depend on y. it's same for all y, and that's something we have seen before. So this shows that P2 distribution of T0 is same as that of the sum of two independent random variables, each distributed as P1 distribution of T0. So the claim is proved, of course, for y equal to 2, but for any general y, it's the similar proof. So now if you use this in this equality, that gives you expectation E0 of T0 is 1 plus summation y greater than or equal to 1 y theta y into E0 T0, which is same as 1 plus mu into E0 T0, which results in, of course, assuming that mu is less than or equal to 1 so that the chain is recurrent. We have just proved this. From this you can easily conclude that if mu is 1, then the only way this equality can be true is if E0 T0 is infinite, whereas if mu is strictly less than 1, in that case from this equation you get E0 T0 is 1 over 1 minus mu, which is finite. So what's the upshot? The upshot is that if mu is 1, mu greater than 1, we already know that we don't have to do anything because the states are all transient. So mu equals 1 means states are null recurrent and therefore no stationary distribution, and mu less than 1 means states are positive recurrent, therefore there is a unique stationary distribution. Okay. So at least we have seen that for only mu less than 1 you have a unique stationary distribution. The question is, what is the stationary distribution? Well, solving pi equal to pi p, or equivalently pi y equal to this equation, which is just breaking down the matrix equation into linear equations, system of linear equations, solving this directly is difficult. Instead, what we could do is we could denote gs and phi s to be the probability generating functions, something that we have already introduced before, of the distributions pi and theta respectively. So pi here is the stationary distribution and theta is the distribution of the number of arrivals per unit time for any period. So gs is this, pi s is this. Multiplying both sides by pi y, you would get, that means, so multiplying, if you look at this equation, you multiply both sides of this by sy and then sum over all y and simplify, you can end up getting this equation. So convince yourself, it's just a little bit of algebra, but we know that pi 0 is 1 over E0 T0, which is 1 minus mu inverse. So if you look at pi y, you can easily obtain it. We are not going to really derive this, but you can obtain it by using the formula that any pi y, because you have now the probability generating function of pi, so you know how to get the individual probabilities from that generating function. So you have to take successive derivatives of that function at 0 and then divide by y factorial. So pi y is the yth derivative of g at 0 divided by y factorial. We are not going to explicitly write down the formula, but that's basically how you get it. So this is basically something that shows you, number one, in the queuing chain, for if the is the expected number of arrivals during a unit period of time, expected number of arrivals is greater than 1, then you have transients, no stationary distribution. If expected number of arrivals is less than or equal to 1, then of course it's an irreducible recurrent chain. But even then, if that expected number happens to be 1, then it's a null recurrent irreducible chain, so no stationary distribution. So the only case when the states happen to be positive recurrent is when the expected number of arrivals is strictly less than 1, and in that case there is a unique stationary distribution, and this is a method of finding the stationary distribution if you are interested in. In this lectures, what we have really seen is we have studied several examples. First two examples were those of finite state space irreducible Markov chains, in which case we knew that we do have a unique stationary distribution. That was never the question. So the question was, how do we go about finding the unique stationary distribution? Now, of course, that we did by actually solving the equation pi p equal to pi. But most important thing, or one important thing, was that we had to also at some stage use this additional condition that pi is a probability. So in other words, what I'm trying to say is, you cannot solve for the stationary distribution in case it exists simply by solving the matrix equation pi p equal to pi. At some stage, you have to also bring in that additional fact that pi is a probability distribution. Of course, then we moved on to some infinite state space examples. The first was simple random walk. Of course, we don't have to look at the situation where it's an asymmetric simple random walk, because in that case we know all states are transient. Then for the symmetric simple random walk, we actually showed that you cannot have a stationary distribution, which really means that in the symmetric case, the only case when simple random walk is recurrent, all states happen to be positive recurrent. Thereby, upshot is, for random walk, simple random walk, there is never any stationary distribution. Then we looked at two other examples of infinite state space irreducible Markov chains. The most important one was the queuing chain example. Of course, in both the examples, we had to use different kinds of approaches. So essentially, the moral of the story is that depending on the special Markov chain, there is no one method. Okay, there is no one method which will apply to all cases. So each Markov chain demands its own approach, some new techniques, some new ideas by which you can actually settle this question. So I guess these three examples would give you some idea as to how to go about it in general.